In this video, we'll be talking about Hess's law. This is part of the video series for thermochemistry for the basic physical chemistry course at the University of Lagos. So this is another way to calculate reaction enthalpy. Hess's law states that the enthalpy change for a reaction that is carried out in a series of steps is equal to the sum of the enthalpy changes of all the individual steps. And this is because the enthalpy change is a state function. It does not depend on how the state was achieved, it just depends on the state. Consider an hypothetical reaction A that can go to B through several processes. It can go directly to B, and the enthalpy change for that process is H1. It can go from A through C, then to B finally, and the enthalpy change from A to C is delta H2, and from C to B is delta H3. And it can also go from A to D, D to E, and E to B. And A to D, the enthalpy change is delta H4, enthalpy change is delta H5 for D to E, and the enthalpy change for E to B is delta H6. So C, D, and E are intermediates that are finally converted to the reactant product, to the product of the reaction. According to Hess's law, that the enthalpy change for a reaction is the same regardless of the number of steps. So we have that delta H1 is equal to delta H2 plus delta H3, because the final step is A to B, it's just going through C. In a similar way, delta H1 is equal to delta H4 plus delta H5 plus delta HC, because the net reaction is A to B. These individual reactions may or may not be real, but they need to be balanced in order to calculate Hess's law. So for example, the direct conversion of CH4 plus 2O2 to CO2 to give 2CO2 plus 2H2O, it can go stepwisely. So the net delta H1 is equal to delta H2 plus delta H3. So minus 890 is the same thing as minus 607 and minus 283 together. When using Hess's law, we have to consider some properties of delta H, because it is an extensive property. Whenever we multiply the reaction by a factor n, then the delta H must also be multiplied by that factor. For example, the combustion of graphite to give carbon monoxide for 1 mole is minus 110 kilojoules per mole. Now, if this reaction is multiplied by 2, maybe it's needed for a calculation, delta H has to be multiplied by 2. When it was multiplied by 6, delta H is also multiplied by 6. So 2C plus O2 to give 2CO2, delta H of formation is minus 220. That's double the delta H for this reaction. Then, reversing a reaction changes the sign of delta H, and that's because it is a state function. So we have C plus half O2 going to CO, and the delta H is minus 110. So if we move from CO back to C plus half O2, so this is delta H, not delta H of formation, please. It's just delta H is 110. So that's the reverse of formation. If we multiply it by 2 again, similar to what we just discussed, then its reverse is now 220. So notice that once we reverse this, the sign of this changes. Here it is minus 110. Here it is 110. It's positive. If there's no sign, then it's positive. So a quick example of how to use delta, the Hess's law. So acetylene cannot be prepared directly from its elements according to that equation. So this is an equation of formation for acetylene, but it usually cannot be prepared. However, we have to calculate the change in enthalpy for this reaction from the following thermochemical equations. Remember, a thermochemical equation has the equation written in it with the species given in their states, gas, gas, solid, and the delta H for the reaction given. So we have this information, carbon to CO2. So we can draw it out. It's always easy to draw it out. We can also write it down. So we have to determine C plus H2 going to 2CS. Okay, so carbon plus O2 to form CO2. So we have 2 moles of carbon here. Here we have 1 mole, so we can easily multiply it by 2. So this is also multiplied by 2. So plus 2 moles of carbon going to CO2. The delta H for that reaction, because we have multiplied by 2, is now 2 times minus 393.5. In a similar way, we are also given H2 going to H2O liquid. So for that reaction, so it's H2 plus alpha2, which is the same thing as what we have here. So it doesn't really matter. So we can take delta H. So that one should be delta H2. It's hidden somewhere. So this is delta H3 for this reaction of H2 going to plus alpha2 going to H2O liquid. That's minus 285.8. Notice that we did not multiply this by any factor because we used it exactly as it is. Now in the final step, we're given the conversion of C2H2 to carbon dioxide. However, we're moving from carbon dioxide and water to C2H2. That's plus 5 over 2, 5 halves. So if you notice, we're using the reverse of this reaction. And since we're using the reverse of this reaction, our delta H is now negative. Is now positive, which was negative is now positive. Remember one of the properties of delta H. And we can now calculate, so we have a reaction, delta H1, delta H2, delta H3, and delta H4. So this is from Hess's law, our delta H1 is equal to delta H2 plus delta H3 plus delta H4, because this has formed a cycle. So we can slot in the values. 2 into 393 minus 0.5 plus 285.8 plus 1299. And I also want us to note this, that 202 plus alpha2, that's a 5 halves. It's nullified here. So the answer is 227. Bond energies can also be used to calculate the reaction enthalpies. The bond energy, the bond dissociation energy is energy required to break a given bond in a specific molecule. So if we look at this, this is a breaking OH bond, that's 477. It's still OH bond, 423. Here we're breaking another OH bond. So the bond dissociation energy is specific to a compound. Bond dissociation energy, that's the energy required to break 1 mole of a specific bond in a compound. When we refer to bond energy, see, we've talked about bond dissociation energy. When we talk about bond energy or bond enthalpy, that's the average amount of energy per mole necessary to rupture a particular bond in a molecule. So it's often given as an average of several dissociation energies. So for example, for OH here, which is 477 in water, it's 423 in hydroxyl ion, it's 429 in methanol. The average over a large number of compounds is mostly given as 443. So bond dissociation energies can be used to estimate bond enthalpy. That's because it's an average of several bond energies. For diatomic molecule, the bond energy and bond dissociation energy are the same, since it's just going to atoms. And then for solid elements, the bond enthalpy is just the enthalpy of atomization, like we discussed in the previous video. The total bond enthalpy of a compound is the energy required to break all its all its bonds in a gaseous compound to separate atoms. So CH4 going to C gas plus. So the enthalpy of this reaction is the bond enthalpy. Is the bond enthalpy of that reaction. Okay, so bond enthalpy in some other places can also be referred to as the energy required to form. So we can talk about bond breaking enthalpy or bond forming enthalpy. So if you note here, the bond formation is negative because formation is always exothermic. Bond dissociation, on the other hand, is positive. This is the dissociation, it's positive. Bond formation is negative. So the bond energies can be used to indicate how stable a compound is. The more energy required to break a bond, the more stable the compound is. Anyway, so how is this related to the enthalpy of a reaction? The bond in a chemical reaction, we know that bonds are broken and then bonds are formed in the product. The total enthalpy of that reaction is therefore the sum of the energies required to break the old bond plus the sum of energies released in the formation of a new bond. Because of that, so the bond of a reaction can be estimated from the sum of bonds broken. So that's the energies of the reactants, because that's what is broken, A, plus the sum of minus the sum of the bonds formed. So A minus AC, that's a bond, plus BD. So these are formed, are broken, and then these ones are formed. So AC is broken to form A plus C, BD is broken to form B plus D, and then we have AB coming together and CD coming together. So the next reaction. So let's work an example on this. Using the table of bond energies are often tabulated as a reference point. Calculate the delta H for the reaction of methane with chlorine to give freon, that's a C2Cl2. So let's look at the reaction CH4 plus 2Cl2 plus 2F2 to give CF2Cl2 plus 2HF plus 2HCl. Okay, so the bonds that are broken, that's 4 moles of, so 4 CH4 here, 4 CH, 2 Cl, and 2F. And the bonds that are formed, if we look at it, CF2, that's 2, CCl2, so that's another CCl, then HF, 2 of those, and 2HCl, 2 of those as well. So that's what we have, bonds broken and bonds formed. From the table, it's always tabulated. From the table, we have so the bonds broken again, CH4, 4 CH bonds, 2 CCl bonds, and 2 FF bonds. And then the ones that are formed, 2 Cl bonds, 2 Cl bonds, and 2 HCl bonds, and the 2 HF bonds. So the delta H of the reaction is bonds broken minus bonds formed. So we can slot that into the equation, 4 times CH plus 2 times CCl plus 2 times F plus, so that's the for bonds formed, brackets closed, minus the sum of bracket open 2 times CF plus 2 times CCl plus 2 times HCl plus 2 times HF, and D here stands for the dissociation energy of the bonds. So we slot in our values from here. So let's see, CH is 413, ClCl is where's ClCl? It's somewhere hidden. So this is Cl, so that's 242. So we calculate everything, we arrive at minus 117 kilojoules. So that's it.